All right, in this section we're going to take a broad look at what functions are. We have some experience with functions already. The sine and cosine and tangent, those are functions that map, we plug in angles and we get out some values. A function is really like a machine or a mapping, and it's a machine that will spit out an output given a particular input, and it has to satisfy one requirement, and that is that for any particular input it can only produce one output, right? There can be no ambiguity about what an output will be given a particular input. So let's say A and B are a couple of sets. We have a function that maps from one set into another set. And this function is a mapping, and this first set that it maps from is called the domain, and it maps into this other set we call the codomain, such that the domain, and each element in the domain maps to one element of the codomain. That's what I was just talking about when I said there can be no ambiguity about what the output will be. Now, the codomain is the set that it maps into. Not every element of the codomain will actually be an output. So if I look at, of the codomain, what are the possible outputs? What are the possible values that I might get out of a function? We call that set the range. And the range is always contained in the codomain, but not always equal to the codomain. And so for kind of one quick example, I'll just do this up here in the margin. If we consider the function, and most functions that we look at, I think probably all functions that we look at will be in the form of an equation, y equals 1 over x. So here, y is the output variable and x is the input. We say that x is the independent variable because that's what we're kind of plugging in to see what happens to the outputs. Y is the dependent variable. So this function maps real numbers to real numbers. Right? The domain and codomain are the same. But the range is not all real numbers. Every output will be a real number, but not every real number can actually be achieved, can actually be spit out by this function. So the codomain is all real numbers. But when I think about what values could actually be hit by this function, what values could be spit out, I can get every real number except 0. So the range is all real numbers except 0. If we think about domain and range, especially when we're talking about functions that map from reals to reals, it can be helpful to consider a graph of this function. And we'll talk about, how we obtain graphs, maybe by doing just plotting some points. But if you, threw this equation, this function into the calculator, it would look something like this. There's our axes. It would look like this. The domain, in this case, are all the x values. So if I think about following this curve, what are all the possible x coordinates? And so if we think about the domain of this function, the possible x coordinates, we get every real number except 0. And the range, again, we get every real number except 0. It never actually crosses that x-axis. We'll talk more about domain and range in a bit, but for now, I just want to kind of focus on what makes something a function. Again, for each input, there can be exactly one output. There can be no ambiguity about what a function will produce once we plug in a number. So here are a couple of equations with x and y. We want to know which equation specifies a function with independent variable x. So if I'm working with an equation, I would say probably one of the easiest things to do is simply solve for y. So in this first equation, we can add 3x. We get 4y equals 3x plus 8. And then once we divide by 4, we get y equals 3x plus 8 divided by 4. So when I look at the equation in this form, right, this is an equation that is all set up to spit out y once I plug in x. And this equation does specify a function. If I take a real number and multiply it by 3, there's no ambiguity about what it will produce. If I take a number and add 8, there's no ambiguity about what the result will be. And likewise, if I take a number and divide it by 4, there's only going to be one possible output. So this equation does specify a function. To see what it looks like when we have an equation that does not specify a function, let's consider the following. Y squared plus x squared equals 9. If I want to solve this for y, we subtract x squared. Y squared equals 9 minus x squared. And then we need to take the square root on both sides. Now, when we're given a square root, when a square root is already a part of an expression or an equation, we know that they're referring to the positive root or the principal root. However, if we are the ones imposing the square root on an equation, if it was not already there to begin with, I have to consider the fact that there are two square roots of every real number. So, or two square roots of every real number if we allow ourselves complex outputs, one square root, two square roots of every positive real number, rather, if we only allow ourselves real outputs. So when we solve this, we end up with y equals plus or minus the square root of 9 minus x squared. So this part right here, this plus or minus, that tells me y is not a function of x. Right? Because once I plug in a value for x, it could give me either the positive or the negative square root. There are two possible outputs. That makes it not a function. So those are some examples to determine that help us determine whether or not an equation defines a function. If we're looking at a graph of an equation, there's kind of a really simple way to determine if what we're looking at is a function. We call it the vertical line test. Remember that to be a function, every input can have only one output, and graphically what that means is that for any x value, like say this x value right here, there can be only one y value that corresponds to it. And we see that happening right here. For any x value, for this x value here, there's only one value. In fact, no matter which one I take, right, no matter which value I take, there's only one y that will correspond. Oops. There's only one y value that corresponds to that x value. We call this the vertical line test. What it means is that no matter which vertical line I draw, it'll only cross the graph once. Compare this to the graph on the right. Here I could see once I pick this x value here, it crosses the graph twice. There's two places where it crosses the graph. So the graph on the right, not a function. In fact, you could see the graph on the right, every vertical line we draw will cross this graph twice. You only need that to happen once. There needs only be one spot where it fails a vertical line test in order for something to not be a function. In this case, we happen to see it failing all over the place. The graph on the left is a function. All right, so back to domain and range. Our basic assumption in this chapter is that we are working with real valued functions, meaning my domain, I'm only considering real inputs, and my outputs, I'm only considering outputs that are real. So if we go back to this example back here, I at first said, every number has two square roots, and that's only true if we consider complex outputs. For the purposes of this chapter, we're working with real valued functions, so only the positive numbers will have square roots. So if we're finding the domain of a function, domain is the stuff we can plug in. we basically kind of come at that question from the back door. We want to know what numbers, to answer the domain question, we want to know what can I plug in. So we just try to find, is there a way I can break this function? Meaning, what are the functions, what are the values that I would plug in that would cause problems? What values can I not plug in? And there's two basic considerations. We can't divide by 0. We can never divide by 0 under any circumstances. And then we can't take an even root, like a square root or a fourth root of a negative number. So in example 9.3, we want to find the domain and range. So we'll just note here that this function, the equation, is not in the form of a fraction. There's no x's in the denominator, so we are in no danger of dividing by 0. So that criteria is all set. Now let's consider the other scenario, or the other problem. We can't take a square root of a negative number. So if I want to consider the circumstances that would lead to this, this clearly, I've got a radical here, I've got a square root involved, and so I need, in order to avoid having a square root of a negative, I need the stuff inside the radical to be greater than or equal to 0. You could take a square root of 0, it's 0, just not a square root of a negative. So I need this to be greater than or equal to 0, which means I'm going to solve this for x. And when we solve an inequality, we always want to keep x on the left. So I'm going to subtract 4. And we get negative x greater than or equal to negative 4. And then if we multiply both sides by negative 1, we get x is less than or equal to positive 4. Remember from way back in chapter 2, I think, when we were looking at solving inequalities, remember that if I multiply or divide both sides by a negative, I have to flip that inequality sign. So this tells me that the domain of this function is the set of all x. So I'm going to use set notation here, and I'll explain what I'm doing in a second. The first thing we do is say all the numbers we're considering. So this would be all the x values in the set of real numbers. That's what that weird looking R is. It stands for all real numbers, like the real number line. And then I say what has to be true about x. So in this case, x has to be less than or equal to 4. Now usually in practice, if I'm just working out a problem, I might just say, oh, the domain is x less than or equal to 4. Like that's the important part here, right, is saying what has to be true about x. Now what about the range, right? So we know that we can only plug in values that are less than or equal to 4. Let's think about the values we might be able to get out. This one is a little bit less, I want to say maybe a little bit less straightforward. With the domain, I just have these couple things I need to consider, right? Check off the list. And even when I considered, taking the square root of a negative, I was able to just sort of make an equation out of that. With the range, we really have to think critically about this function and say what's possible to get out. And we'll note that here y is equal to the square root of 4 minus x. Now that square root was given. We didn't take a square root on both sides. So that is just the positive square root. This is the principal root or positive root. And so that means I'm only going to get positive numbers. So the range is going to be the set of all y in the real numbers such that y is greater than or equal to 0. I can't get a negative result out of this. And in fact, if you threw that function into your calculator, it would look something like this. Okay. All right, so let's do another one. Let's find the domain and range of this function, y equals 3 divided by 2 minus x. Now there's no radicals here, so I know I'm in no danger of taking a square root of a negative. But I've got a fraction, I can see x is in the denominator, so I know there's really a danger, there's a possibility of division by 0. So I need to figure out what would make me divide by 0 and then say our domain cannot include that number. So So all I'm going to do is take that denominator and set it not equal to 0. So I say, okay, well 2 minus x cannot be equal to 0, and that means that x can't be equal to 2. So there's our domain, and so a lot of the time people will just say the domain is x not equal to 2, or I could use sort of the more descriptive set notation here. So I can plug in any real number I want except 2. And now for the range, again, we have to just think critically about what's possible to get out of this function. Now that I'm dividing two things, right? When I evaluate this function, I'm taking the positive number 3 and I'm dividing it by whatever's in the bottom. And I can divide 3 by anything but 0. And 2 minus x can take on a full range of values except for 0. So it can take on positive values, negative values, really small values, really large values. So I can get positives and negatives out of this function. However, when I think about the range, usually, again, I come at it from the back door and I just say, look, is there anything that is impossible to get? I try to find a value that this fraction could never attain. And in this case, the range is all real numbers except 0. And the reason I know that is because a fraction is 0 precisely when the numerator is 0. And, of course, 3 is never equal to 0. So 0 is impossible to get as an output. All right, so now a little bit of function notation. I think we've probably seen this a little bit. In fact, we are already familiar with function notation. Think back to, one of the last times we did, you had to use any, trigonometry, the trigonometric functions. So think of this equation: sine pi over 6 equals 1/2. We could see that, go back to the unit circle here. We know that sine of pi over 6 is equal to 1/2. And when we read this on the left side, we say sine of pi over 6. And that is function notation. So with the trig functions, we have these special notations like sin, cos, tan for sine, cosine, and tangent, respectively. But we can more generally define functions. So often we'll use just the lowercase letter f, or sometimes g or h. And so when we use function notation, we'll often write f of x in place of y. So y is equal to f of x. And when we use this f of x, this is function notation here. It's really important to note that f of x is read as f of x. It does not indicate multiplication, right? Those parentheses is not a multiplication. So, writing y equals and f of x equals, they're really equivalent. And writing f of x equals is just sort of driving home the point that this is a function and we're using function notation. But these define the same functions, right? Just we're using different notations in either case. The reason we have function notation, it does give us some efficiencies. For example, if I looked at the function y equals 3x squared plus 5x minus 6, or f of x equals 3x squared plus 5x minus 6, the phrase find y when x equals 2 is simply written as find f of 2, right? So if I replace x with some value in the parentheses here, that's just telling me replace x with that value everywhere that it appears in the function and evaluate. So here, if f of x is 5x squared minus 4, then f of 0, I'm going to plug in 0 for x. So I think of this function as really like a set of instructions. And wherever an x appears, at first I'll just write like an empty set of parentheses. And whatever goes here I'm going to put there. Now x only appeared in one term, so I only have one set of parentheses to put that in, but even if I had several terms that had an x, I'd have that empty set of parentheses, and I'd put the same value in each time. And this gives us -4. So there's f of 0. F of -3. So plugging in -3 for x gives us what? That's 9 times 5 is 45, minus 4 is 41. So f of -3 is 41. F is a common letter to choose, F for function, but of course you could pick any letter you want. G and H are also pretty common. Whenever you're working with more than one function in the same problem, you absolutely cannot use the same letter to represent two different functions in one problem. So it's important to make sure that you don't have redundancy there or ambiguity about what the function f refers to. All right, so some more examples. Here I've got the function f and this other function g. So when in each of these examples they're asking me to evaluate a function, they're telling me which function to use and what value to plug in. So here I'm going to use the f function and I'm going to plug in 6. So 12 divided by 6 minus 2, 12 over 4, that gives us 3. G of -2 says I'm going to use the g function and I'm going to plug in -2, so that is the square root of -2 minus 1, which is the square root of -3. And in this chapter, if we're really considering just real valued functions, we would say that g of -2 does not exist, right? Because this is not real. So g of -2 does not exist. And another way to say that is that -2 is not in the domain of g. Now, if we're allowing functions to be complex valued, then we could say that this is the same as root 3 times j. We've already, learned quite a bit about complex numbers. And then in part C, f of 6 times g of 2. So I'm going to find f of 6, I'm going to find g of 2, and then I'm going to multiply them together. We've already found f of 6 up here, that's 3. G of 2 we still need to find, so maybe I'll do this on the side. That's the square root of 1, or just 1. So f of 6 times g of 2 is 3 times 1, or 3. So far we've just plugged in numbers to our functions, but we could also just plug in other expressions. If I want to plug in f of 3c squared, then wherever I see my variable x, I'm going to replace it with 3c squared. So again, I'm going to start out, my f of x is x squared minus 4x. So whatever my input is, I'm going to square it, and then I'm going to subtract 4 times the input. And now here, my input is 3c squared. I'm going to do some algebra using our rules of exponents. So we've got, let's see, 3 squared is 9c squared squared. I multiply the exponents, that's c to the 4th. And then 4 times 3c squared is 12c squared. And that is the result. There's really nothing else to do. We're obviously not going to get a numerical answer out of this because we don't know what value c takes on. If I want to find f of a plus 5, again, I'm going to start out seeing the function as a set of instructions, and wherever I've got an x, I'm going to put this empty set of parentheses. Here I'm on the left side plugging in a plus 5 into the parentheses, so I'm going to do that on this side. And now I'm going to just expand. So a plus 5 times a plus 5 is a squared plus plus 10a plus 25. I'm going to distribute this negative 4, so minus 4a minus 20. And then simplify. I'll combine like terms, a squared plus 6a plus 5. And there is f of a plus 5. We could leave it there, or I think this expression actually factors, so you could also write it as a plus 5, a plus 1. I think either is fine. Okay. So now we know how to plug in, what it means when we say find f of 6. We know what it means when we say find f of a plus 5. We can plug in whole expressions into a function. Now we're ready to talk about function composition. So in this abstract sense, right, a function maps from one set into another. And if our codomain of one function, the set it maps into, matches up nicely with the domain of another function, then we could sort of have this bit of like a leapfrog function. We call it the composition. So in this definition, we have G mapping from A to B and F mapping from B to C. So note that wherever G maps into lines up with where F maps from. Right, so once I get from A to B from the G function, then F can pick up where it left off. I'm going to kind of just draw this out at, just a picture of what this looks like. So here's a set A, here's a set B, here's another set C. And for us, likely the domain and codomain of most of our functions, or all of our functions, are at least contained in the real numbers. They could be smaller, they could be subsets. So in this definition, they're telling us that G maps from A to B, and F maps from B to C. So if I take some element of A, then I can apply the G function to that, and it'll send me somewhere over here in the set B. So this is G of A. But now G of A itself is in the set B, which means I can apply F to it. So once I apply F, that'll send me somewhere to in C. So I've applied F to the value G of A. And that's F of G of A. And we say that this function, once I put these functions together, I basically created a new function that maps from A directly into C. And that is the composition F of G. And we use that little circle in between to denote a composition. So this here it is in the definition, the composition from A to C, which we denote as F of G. If A is an element of A, then F of G of A is just F of G of A. And when you look at a composition like this, the innermost function, that's applied first, and then you do this one last. So in example 9.8, F and G both map from reals to reals. So note that the codomain of F, the codomain of G matches up nicely with the domain of F. F is the function 1 minus 2x. G is the function 3x squared minus 5. And we want to find the function f of g. So f of g of x is equal to, the first thing I'm going to do is just rewrite it the way that it suggests in the definition, f of g of x. And this means that I'm taking the g of x function and I'm plugging it into the f function. So this is f of 3x squared minus 5. Now, I know how to plug in an expression to another function. Right? I'm going to take the f function, 1 minus 2x, and I'm going to plug in 3x squared minus 5. I'll do some algebra, distribute that -2, and and we get 11 minus 6x squared. So this is f of g of x. That's the composition function. Now, just to see what we mean by a composition function, suppose I wanted to find f of g of 3. On the one hand, we could say, all right, well, what's g of 3 equal to, right? So g of 3 is 3 times 3 squared minus 5. So that is 27 minus 5, which is 22. So f of g of 3 is f of 22. And if I plug in 22, I get 1 minus 44, which is negative 43. So this is, when we do a composition of functions, what we're saying is, apply the inner function first, right, and then plug that into your outer function and see what you get. When we figure out what the composition function is, just as a function of x, we're saying that's the same thing as just plugging in this input 3 into this expression, 11 minus 6x squared. Six times 9 is 54, and that is negative 43. So these match up. Now, in this case, this is not always the case, but in this case, because both functions map from reals to reals, the compositions in both directions are defined, right? So we just found f of g. Now we can find g of f. So g of f of x is g of f of x, and that means I'm going to take the g function and plug in our f function, and our f function is 1 minus 2x. Now the g function is 3x squared minus 5, so 3 times the square of our input minus 5. Let's see, doing some algebra. If you FOIL out the 1 minus 2x times 1 minus 2x, you get 1 minus 4x plus 4x squared. And then we're subtracting 5. We can distribute the 3 and then combine like terms. So we get 12x squared minus 12x minus 2. So this is g of f of x. Now compare these two results. There's f of g of x, there's g of f of x. If you just compare these two expressions, it takes just a couple seconds to realize that they're not equal, right? Since they're not equal, then the observation that we can make on this is that the order in which you compose functions matters. In other words, function composition is not commutative. Okay, so the last thing we'll do in this section is just talk about graphing a function by plotting points. We've done this before. I think we did it actually when we were graphing the trig function. So we kind of know what we're doing when we say plotting points. We're saying let's let x range through a variety of values, and then see what y values we get out as an output, and each pair gives us a point we can plot, and then we connect them. And it's important to connect them in a smooth curve. These are nice, smooth, continuous functions. They're not just composed of straight line segments. It's graphing a function, it's not connect the dots. So if I wanted to graph the function 9 minus x squared, so one thing I can do, just maybe to help organize, is make a table. And I'll let x range through a variety of values. You know, when we did the trig functions, it would suffice to just go once around the circle, right? That would give us the whole range of outputs. Here, we don't quite have such a nice simple observation to make that will help us there. So what we want to do is just grab a variety of values, make sure you give yourself some negative, some positive, you know, think about what the domain is, and then grab a variety of values in that domain. I don't need to plot 100 points, I just want a few to kind of give me a sense for what this looks like. So I'm going to just go from -4 to 4. And then I'm going to find the y value. So when x is -4, we get 9 minus -4 squared. 9 minus 16 is -7. And that gives us the point, xy point, -4, -7. And I'm just going to plot, I'm just going to do these out and write out all the coordinates. And then once I see what the range of outputs is, then I will have a better idea of like what scale I'm going to use on my axes. So when I plug in -3, -3 squared is 9, and 9 minus 9 is 0. 9 minus 4 is 5. 9 minus 1 is 8. 9 minus 0 is 9. And then 9 minus 1 is 8. Okay, so you might have already noticed, you know, look, the only place that x appears is where x is being squared, so it's going to give the same value when I plug in a positive as when I plugged in the negative. So the rest of these we can kind of breeze through because we should just get the same values repeated back to us as we got before for the negatives. So then our points are -4, -7, -3, 0, -2, 5, -1, 8, 0, 9, 1, 8, 2, 5, 3, 0, 4, -7. All right, so on the x-axis, I think I'll take 2 little squares for each unit. But I need to go up further and down further on the y-axis, so I'm gonna just do a 1 for 1. So there's 9. And then the others were 8 and 5. Okay, so 0, 9. 1 and -1 both map to 8. 2 and -2 both map to 5. And 3 and -3 both map to 0. And then 4 and -4 both map to -7. So now we have these points, and what's important is to do our best to connect them with a continuous curve. And then also notice what I'm doing on the end. I'm not just ending at those last dots. What I'm doing is I'm observing a pattern, and then to the best of my knowledge, that pattern continues, and that makes sense, right? As x gets bigger in either the positive or negative direction, we just keep subtracting bigger numbers, so the function values should grow larger in the negative direction. And I want to indicate that. I don't want to just end, like if I just ended like this, what I would be saying to the reader or to anybody looking at my work is that the function just ends. Like it would suggest that the domain is only from -4 to 4, and we know, looking at this function, I can plug in anything I want. There's no danger of dividing by 0. There's no danger of taking a square root of a negative, right? We can square anything we want. So I want to make sure that I observe the pattern and then indicate that that will continue.